Hello and welcome to this next lecture on the reactions of period 3 elements. Now, this is basically a continuation of what we did in the previous lecture. We were speaking about the acid-base nature of the oxides of period 3. And we found that the acid-base nature of aluminium oxide and silicon dioxide could not be discussed because they do not react or they do not dissolve in water. Okay. So it's difficult to find the pH of those solutions, okay, because they actually don't form solutions, okay, aqueous solutions, that is. But there is a way of ascertaining the acid-base nature of aluminium oxide and silicon dioxide, and that is taking a leaf out of our discussion on the nature of oxides in IGCSE, where we talk about how amphoteric oxides react with both acids and bases, alkalis, while acidic oxides only react with alkalis, while basic oxides only react with acids. So we try that method. Okay. So if you look at aluminium oxide, aluminium oxide, or rather, let's talk about acid-base nature of Al2O3 of aluminium oxide. Right. You take aluminium oxide. Okay, let's forget for a minute that aluminium oxide is amphoteric. Let's assume that we don't have that information with us. So what I can do is I can take aluminium oxide and react it with a strong acid like hydrochloric acid. Yeah. So take aluminium oxide and I react it with a strong acid like hydrochloric acid. And that gives me the salt, aluminium chloride, and water. So that's a classic neutralization reaction where the aluminium oxide is acting as the base with the hydrochloric acid to produce the salt and water. That shows that this is acting as the base, while this is acting as the acid. Okay. Similarly, when you take aluminium oxide and react it with a strong alkali like, say, sodium hydroxide. Actually, you have quite a few reactions where aluminium oxide reacts with a strong alkali like sodium hydroxide. It forms compounds which are commonly called as aluminates, right? Compounds called as aluminates. The ATE ending tells you that aluminium is combined with oxygen, and also that aluminium is part of a overall anion, a negative ion. So aluminium oxygen put together anion. Okay, so there are quite a few because the reaction seems to vary depending on conditions like temperature. But a standard one that we can use, okay, and one that is quite simple as well, is that it basically combines with sodium to form sodium aluminium hydroxide, NaAlOH4. All right, you basically have NaAlOH4, which is formed when the sodium hydroxide reacts with aluminium oxide. In this case, this is acting as the base, so the aluminium oxide is acting as the acid. As a result, this proves that, okay, since aluminium oxide reacts with both acid and alkali, okay, it is amphoteric. It is amphoteric. We can have a similar discussion on the acid-base nature of silicon dioxide, or silicon 4 oxide as it's called, SiO2. Okay, SiO2. Remember, SiO2 has got a giant macromolecular covalent structure similar to that of diamond. Okay, it's a tetrahedrally held structure. All right. If you take silicon dioxide and react it with a strong acid like, say, HCl, yeah, you take silicon dioxide and you react it with a strong acid like HCl, no reaction is seen. Okay, no reaction is seen. That kind of tells us that silicon dioxide does not act as a base, so it's not a basic oxide. But on the other hand, if I take silicon dioxide and I react it with an alkali like sodium hydroxide, you get sodium silicate, the salt sodium silicate, and water. Okay, you get the salt sodium silicate and water. Okay, that tells you that if this is your base, here silicon dioxide is acting as the acid. Okay, that is the acid. Now, from your IGCSE days, you would have come across this reaction when silicon dioxide present in sand reacts with basic oxide, calcium oxide, to produce calcium silicate, okay, which is your slag. That again is a neutralization reaction showing that silicon dioxide is acting as the acid. Hence, silicon dioxide, okay, silicon dioxide, SiO2 or silicon 4 oxide is an acidic oxide. Okay, it's an acidic oxide. Now, drawing your attention to our discussion earlier as to how bonding affects the basic or acidic nature of the oxide. Let's say you start with sodium oxide. It's strongly acidic, strongly basic, and it's also a strongly ionic compound. Magnesium oxide, okay, is basic, but you see that it's a weaker base compared to sodium oxide. Aluminium oxide is basic, but can also act as an acid, hence it is amphoteric. So you find that even though you have sodium oxide, magnesium oxide, aluminium oxide, right, you find that they are becoming less ionic and more covalent. Okay. In our discussion on polarity, we would have said that very few bonds are 100% ionic, 100% covalent, and that's what happens. Okay. Sodium oxide is pretty strongly ionic. Okay. It's as close to perfect ionic as it gets. All right. While magnesium oxide, the ionic nature decreases, the covalent nature slightly increases. And it keeps increasing. Say covalent nature further increases for aluminum oxide compared to say magnesium oxide. All right. Now, why? If you look at it, okay, the elements sodium, magnesium, aluminum, yani the oxygen is the same, right? The oxygen is the same. The bonds are between sodium and oxygen, say magnesium and oxygen, aluminium and oxygen. Okay, I'm actually technically making a mistake here because I'm drawing it as if it's a covalent bond. It's not. Okay, it's a bit more complicated than that. But I want to draw your attention to the electronegativity of these elements. The electronegativity is 3.5, yeah, for oxygen. That's the electronegativity. While the electronegativity of sodium is 0.9, magnesium is 1.3, aluminium is 1.5. Say 0.9, 1.3, 1.5. So you find that the electronegativity of the metals keeps increases as we move across the period, but the difference in electronegativity decreases. Okay, difference in electronegativity decreases, and we know that the difference in electronegativity must be pretty high for a bond to be ionic. We say that it should be, the difference should be more than 2. Of course, yes, they are all more than 2, but you can also see that as you go from the left to the right, the difference in electronegativity decreases. As a result, bond becomes less ionic and more covalent. All right, less ionic and more covalent. As a result, it tends to go from being more basic towards more acidic. When it comes to, say, silicon 4 oxide, silicon dioxide, the difference in electronegativity is so less that the bond becomes totally covalent. Okay, so this is another classic example of where the bond is not 100% ionic or 100% covalent, but it shows a continuum where it is partially ionic, partially covalent, and the percentage that it is ionic keeps decreasing across the period, while the percentage that is covalent increases across the period. Okay, and that's the reason why it gradually changes from being more basic to being more acidic as you go from left to the right. All right, and that wraps up our discussion on the acid-base nature of aluminum oxide and silicon dioxide.